Let's take a look at this diagram. At the x-axis of this diagram, you have aorta, large arteries, small arteries, all the way to the vein. This shows the sequence of the blood vessels in our body. And in the y-axis, you can see the pressure. Don't worry about these green lines here. Let's focus on this solid black line. As you can see, at the beginning of the aorta, the pressure is 100. As we go through these blood vessels, from the aorta to large artery to a small artery, the blood pressure is not changing that much. Why not? Well, because these vessels, they have lots of elasticity. So think about it. If blood comes inside the vessel is going to bulge. And then when the vessel is going to rebounce, it's going to push the blood forward. So pretty much the pressure is going to stay the same until we get to the arterial. Realize at the level of arterial, the blood pressure is going to drop dramatically. Why? Because arterial has sphincters. And remember I said this one before, that sympathetic works on the arterial system, and as a result, your arterial is being constricted and blood pressure is going to drop. Why do we have to drop blood pressure so low in the arterial system? Because right after arterial, we have capillary. And capillary is only one layer vessel, is very thin. If the blood is going to get inside the capillary with a high pressure, capillary is going to rupture. We have to use arterial as a gatekeeper. So blood pressure is going to drop dramatically in the arterial. By the time blood is going to get to the capillary, the blood pressure is around 30 millimeters of mercury. And when the blood leaves capillary, as you can see, blood pressure is around 10. So the average blood pressure inside the capillary is somewhere between 30 to 10 millimeters of mercury. After that, gradually the blood pressure is going to drop until we're going to get to the end of the vena cava, which blood pressure is going to get close to the zero. You remember we said that in a series system, the blood flow stays the same. So blood is going to go from the large artery to small arteries to arterial to capillary, venule and vein, just like this one. That's a series system. And we said the blood flow in this series system is going to stay the same. As we go through this series of vessels, when we get to the arterial, the resistance inside the artery is going to go up very high. And remember, Q is equal to P divided by R. So therefore, P is equal to Q times R. If R goes up and Q stays constant, then the P downstream of the vessel must go down. Remember, the way that Q works is if I have a tube and pressure here and here, at point 1 or 2, they stay close to each other, blood is not going to flow. But blood is going to flow if the point number 2 has a lower pressure. So if my resistance goes up, then the only way to keep my blood flow is decreasing this pressure lower, so blood is going to flow. So necessarily my P must go down. The pressure inside the artery follows the cardiac cycle. Remember, the cardiac cycle is composed of contraction and then relaxation. Your arterial pressure follows the same pattern. So when the ventricle is going to go to contraction and push the blood inside the aorta, the blood pressure is going to go up. Then when the ventricle starts relaxing, now blood wants to come back. As a result, pressure inside the aorta is going to drop. However, as soon as blood is going to come, it's going to hit the aortic valve to close, and blood is going to hit the aortic valve and it's going to bounce back. As a result, it's going to create this blip here. This small blip here is called necrotic notch. And after that, again, blood is going to start leaving the aorta, therefore the pressure inside the aorta is going to come down. That's during the heart relaxing. For one more time, when the ventricle goes to contraction, push the blood inside the aorta, pressure inside the aorta is going to go up. When the ventricle starts relaxing, pressure inside the aorta is going to go down. Blood wants to come back, and that is going to close the aortic valve. But as soon as it's going to hit the aortic valve, it's going to bounce back. As a result, it's going to create a small increase again. That is called necrotic notch. But after that, blood is leaving the aorta, so pressure inside the aorta is going to go down. During this time, remember, heart is relaxing. That is going to bring us to a term called pulse pressure. A pulse pressure is a difference between systolic pressure minus diastolic pressure. When the heart is relaxing, the pressure inside the vessel is called diastolic pressure. As soon as the heart goes to contraction and push the blood inside the aorta, it's going to create systolic pressure, as we know. The difference between systolic pressure and diastolic pressure is the amount of volume that we pump inside the aorta. So therefore, we say pulse pressure reflects the stroke volume. We use pulse pressure as an indicator of a stroke volume. Remember about compliance? Remember compliance was equal to V divided by P? Assuming the compliance of the aorta is constant, the more volume you're going to put inside the aorta, your pressure is going to go higher. Therefore, I say pulse pressure is going to change for two reasons. Either if the amount of volume that I'm putting inside the aorta is going to change, or if the compliance is going to change. If the compliance of the aorta goes down by any small amount of volume, the pressure is going to increase. So therefore, we would say in a normal person, the pulse pressure should be around 60. Why? Because if the pulse pressure goes high, that means the compliance of my aorta is declined, because by adding a stroke volume inside a vessel that is not very compliant, my pulse pressure should rise even higher. Pulse pressure is important to evaluate your cardiovascular health, because pulse pressure increases if your compliance decreases. Although pulse pressure increase if the stroke volume increase also, but remember, stroke volume in average person stays the same. So if the stroke volume stays the same, but your pulse pressure goes up, they can be only for decreasing of compliance. The next terminology that I want you to know is called mean arterial pressure. It's a mean arterial pressure during your cardiac cycle, but is not simply a mean number. To measure mean arterial pressure, we can take 2/3 of diastole and add it to 1/3 of systole. But why 2/3 of diastole and 1/3 of systole? Well, because heart is going to spend more time in diastole than systole. So the average pressure inside the cardiac cycle should reflect time that heart stays inside one cycle or the other. Since heart stays in diastole twice as long, so therefore we say mean arterial pressure should be 2/3 of diastole and 1/3 of systole. We can measure mean arterial pressure by taking the pulse pressure, get 1/3 of it, and add to diastolic pressure. For instance, if someone's blood pressure is 150/90, to take mean arterial pressure, I'm going to take 1/3 of systole, which is 50, 2/3 of diastole, which is 90, and that is going to be my mean arterial pressure, right? So 1/3 of systole, 2/3 of diastole. Or I can get pulse pressure, which is 150 minus 90, which is 60, and then divide this one by 3, is going to be 20. That is my 1/3 of pulse pressure, and I'm going to add it to diastole. That also is going to bring me to 110. So there are two ways to get mean arterial pressure: 1/3 of systole plus 1/3 of diastole, or get your pulse pressure, divide by 3, and then add it to the diastole. Do you remember this diagram? Remember we talked about this dark line. Now let's talk about this green one. This green one really shows the pulsation inside your vessels. The top one shows the systolic, the bottom one shows diastolic. As you can see in this diagram, the systolic pressure is higher in the large artery compared to aorta. You may tell me this doesn't make sense, because if this is the beginning of the aorta, here's the aorta, and here's a large artery. If systolic pressure here, systolic blood pressure here is higher than here, how blood is going to move from aorta to the large artery if the pressure, systolic pressure here is larger? Well, the answer is diastolic pressure is lower too. So systolic pressure went up, diastolic pressure went down. Therefore, the pulse pressure is bigger in the large artery compared to aorta. My pulse pressure is larger here, yet my mean arterial pressure is lower, because mean arterial pressure mainly depends on what? Diastolic. And since my diastolic pressure is lower inside the large artery, therefore my mean arterial pressure also is lower. Remember, the reason blood moves is not because of systolic pressure, is not because of diastolic pressure, it's because of mean arterial pressure. Blood moves because here should have lower mean arterial pressure, here should have higher mean arterial pressure. So let me repeat one more time. Systolic pressure in the large artery is higher than aorta. However, blood should move from aorta to large arteries. If the systolic pressure in large artery is higher, how come blood moves? And we said the answer is blood does not move because of systolic pressure. Blood does not move because of diastolic pressure. Blood moves because of mean arterial pressure. Mean arterial pressure is a force that moves blood forward. And the mean arterial pressure at the large artery is smaller than aorta. Why? because diastolic pressure in the large artery is lower than aorta. And remember, to measure mean arterial pressure, we're going to use diastolic pressure more than systolic. So therefore, mean arterial pressure at the large artery would be lower than mean arterial pressure of the aorta. As a result, blood is going to move.